I am Shubham Jain, a PhD student at Imperial College London, and today we're talking about the robustness of client-side scanning for illegal content detection on end-to-end encrypted platforms. This work was done with collaboration with Anna Maria Cretu, my fellow PhD student, and advisor Eva Alexandre Monjoy at Computational Privacy Group at the ICL. And before I start, I'd like to thank the AI Village community and DevCon community for providing me the opportunity to present this work. And just to mention before we start that this work is currently under review at a security conference. So let's begin. End-to-end encryption is becoming the norm today. It started in 2013 with Tech Secure, then or Signal today releasing the end-to-end encrypted messaging protocol, and in their app, which was then 2014 adopted by WhatsApp as well as Telegram. In 2016, it was adopted by Messenger for secret chats, and now there are more than 2 billion users who use end-to-end encrypted messaging platforms on a day-to-day basis to communicate with each other. And by 2022, the incredibly popular messaging platforms like Instagram and Messenger might adopt the end-to-end encryption platforms by default. And so end-to-end encryption provides the users to communicate securely. What does this mean? Is that, let's say I want to send a message about, let's say DEFCON is awesome to my friend, and end-to-end encryption ensures that no one apart from my friend and me can read this message. And the way this happens is that there is a shared key using which the message is encrypted. This is then sent to a server who then routes this message to my friend, and my friend has the shared encryption key as well, with which it can decrypt the message and read it. And not just messages, you can also send images using this end-to-end encryption messaging platforms. But this has raised concerns that end-to-end encryption messaging platforms can be used to send illegal content, and this illegal content goes undetected through the servers because the server which is routing the packet does not know what is in the content. It cannot decipher the content itself, the sent packets. And so to solve this problem of how do we detect illegal content and prevent people from sharing it, one of the earliest solutions that has been proposed are key escrow systems, where all the keys are stored in some escrow or a storage, and in some exceptional circumstances, the third parties, like for example law enforcement agencies, can ask the access for these keys. And this has raised significant privacy concerns in the community, where the biggest concern is that it is impractical to build such key escrow systems for large-scale data, and further to ensure that these systems are secure, and then also ensure that these cannot be abused by any public or private organizations. And these concerns lie under the several observations and experiences that we have seen over the years whenever such systems have been developed and deployed. So, to solve this problem, the other solution that has been proposed in last couple of years is client-side scanning. Several researchers and policymakers have proposed client-side scanning as a privacy-preserving solution to detect illegal content. And the way this proposed system would work is, let's say if I want to send a message, now before this message is sent, there will be a digital fingerprinting algorithm in my app which will convert this message or this photo into a fingerprint. This photo would then be checked for a match against a database of already known illegal images. If a match is found, then the message is prevented from being sent and some further action is taken. But if no match is found, then you can send the message as usual. Basically, it's encrypted and then sent. So the client-side scanning has raised some privacy concerns again with the community, and these underlie and two main facts. Firstly, it will increase the attack surfaces. Now there is a digital fingerprinting algorithm which is scanning, matching against the database and sending it to some and flagging the resource. So this increases attack surfaces that can be abused by an adversary. The next biggest concern that has been raised is with respect to the mission creep. So here the question is, who controls the database? What is inside the database? It starts from let's say it will start from the illegal content, but can the system be made abuse resistant, or can it be abused further for different purposes, starting from what governments would want? And so given this, what the question that we ask now is, can an adversary evade detection by client-side scanning? For example, if I want to send this image, which if I sent would be flagged. So as an adversary who has this black box access to digital fingerprinting algorithm to the CSS system, what I want to do is change this image with a small perturbation such that my fingerprint is now not detected by the system and I can bypass detection easily. So the question that we are asking here is basically, is client-side scanning a robust solution? And to answer this question, first we look at what are the current CSS proposals. And the current proposals rely on perceptual hashing algorithms. These are standard image fingerprinting techniques that have been used over the last decade for efficient image search and image retrieval. And it allows to measure image similarity without access to images. So basically you measure image similarity using their fingerprints, where supposedly fingerprints might not reveal anything about the actual image. So it provides some amount of privacy. So for example, and why the way the perceptual hashing algorithms work is that you have this image, the algorithm will produce a fingerprint. Now let's say if I were to modify this image with standard transformations like resize it, grayscale it, change color, then this would result in a fingerprint which would be very similar to the original or same with the original fingerprint. But if there was a completely different image, then that would result in a completely different fingerprint. And Facebook's PDQ is one of the commonly used open sourced perceptual hashing algorithm. So now we know how to create fingerprints. The next question is, how do we find a match? What exactly is happening? And the way this works is that if, let's say, I have a database of fingerprints, I send my image fingerprint, and if distance between the sent fingerprint and any fingerprint in the database is less than a predefined threshold, then I would say a match is there, a match is found. Else, I would say if there is no match found, they will say no match found. So the way the distance metric will work, for example, here in case of a binary fingerprint, I will try to see how many pixels are different between the two fingerprints. And if that number of pixels is less than a threshold, I will say there is a match. And if it's a safe image, ideally we would want it to not be found a match. Safe image is the image not in the database. So we will call it a true negative. If it happens, no match is found for that. If a match is found, we will say it's a false positive. Similarly, for illegal image, ideally want a match to be found, so that's a true positive. If no match is found, we say it's a false negative. and a threshold T is chosen such that it tries to balance between the false positives and false negatives. And we know that increasing the threshold T would lead to more images being flagged as positives, so more false positives and lesser false negatives. Facebook's PDQ, which can have a distance from 0 to 256, recommends a threshold of 20 to 90 for the efficient and good working of the system. So now we redefine our question that can an adversary evade detection by CSS? And we say that, okay, now what we want to do is that can I add a small perturbation such that my resulting hash is at a distance of greater than a threshold T, which is selected or chosen by the adversary who has the black box access to the system, and this we believe might help to further it to evade detection. And we use standard black box ML adversarial ML algorithms, and we show that more than 99.9% of images can be modified successfully for 5 popular hashing algorithms and a wide range of detection thresholds. So we ran this on an ImageNet dataset, and we adapted the approach from Ilyas et al. From the work done in 2018. And the images look like this. So you see we show these images when the PDQ was attacked for different thresholds. At the top you can see the images that were for threshold 30 and 70. At the bottom you can see like for a single image when it was attacked for 4 different increasing thresholds. And we see what this shows is that our attack does not modify image significantly. The two images are still very similar. So with just a very small perturbation, we can possibly find or perturb the image such that the resulting hash is greater than the threshold T. And so next question we ask is basically, is pushing the hash beyond the threshold enough to evade detection? Because that's what ideally we are interested in. We want to evade detection, but we are not matching against just one fingerprint, but against the whole database. So to do this, we look at the false negative rates, which is the probability that a modified illegal image evades detection. Ideally, we want this to be 1. What we see indeed is that for a smaller threshold like 30, 97 of 100 modified illegal images evaded detection when we chose for a database size of 100,000 images selected from the ImageNet dataset, chosen at random. And we see that as the threshold goes from 30 to 90, the number of images that are modified evading detection falls down from 97 to 67 out of 100, which is still very significant. It shows that as the threshold increases, the attack indeed becomes a bit difficult to perform, a bit ineffective, at the same time not very ineffective. So the next question we ask is that, is increasing the threshold an effective defense strategy? And to do this, we measure false positive rates, which is the probability that a safe image is detected falsely. And ideally, we would want this probability to be very low, which we see with the threshold of 30. Again, we use database size of 100,000 images chosen at random from the ImageNet. And we see that for a smaller threshold, 1 out of 1,000 safe images are falsely detected, which is not such a large number. And as the threshold increases to 90, we see that every third image, safe image, is falsely detected, which makes the system not very useful anymore if every third safe image you're sending is being flagged. So increasing the threshold is not really an effective defense. So, okay, but what if the algorithm to attack is public. Our adversarial attack is public, and someone can, on the defense side, who is making these systems, the client-side scanning system, can devise create an adversarial image for all the images in the database and add the hashes of the adversarial image to the database and further basically expanding the database. Would this be an effective defense? To answer the question, we first look at, can our attack produce multiple perturbations? Because if our attack produces only one perturbation, then indeed just adding the hash of the adversarial image to the database would be an effective defense. But unfortunately, our attack can indeed produce multiple perturbations. So the next question we ask is, how diverse are the perturbations? Basically, let's say if all the perturbations that we have result into the hashes which are very close by to each other, then maybe that's not a very effective perturbations out there. Maybe as a defense, again, someone can add just one of the perturbation, and that will detect all other adversarial images that will be generated. And so basically we measure diversity between the perturbations by measuring distance between the hashes of the adversarial images. And what we see is that for even smaller thresholds like 30, we see that a lot of adversarial images result in hashes which are beyond the threshold or distance of t equal to 30 from some other hash some other hash in the adversarial image, which means our hashes are widely dispersed around the space. So adding one hash to the expanded database is not a good defense. So to conclude now, what we saw today is basically three main points. Firstly, client-side scanning is proposed as a privacy-preserving solution to detect illegal content on end-to-end encryption platforms. This system is not a robust solution, and almost always an image can be modified to avoid detection even in a black box setup, which is the proposed way it will be deployed. And finally, the defenses to improve the robustness of such CSS systems, like increase the threshold or expand the database, they don't work against the particular attack. Our paper is available on arXiv. It is currently under review. You can take a look. If you have comments, do tag us, do let us know. You can tweet about us, tweet to us directly on Twitter. We'll be happy to reply back. And before we end this, I think last week something very important happened with respect to what we are discussing today. A lot of this client-side scanning when we started this work was mainly in the proposals through researchers and policymakers. But last week, Apple's Matthew Green, a cryptographic researcher from Johns Hopkins University, revealed that he had a confirmation that Apple is releasing a client-side scanning tool for child sexual abusive media detection. And further, Apple confirmed that it is indeed will begin to start scanning the iCloud photos on the devices using a system, and they released the technical details for it, which shows that these systems are coming on our phones, and might indeed be an important very important conversations for us on how do they really handle the privacy well, and are these systems robust? Now we know a lot more about them in terms of technically. So I leave you with this thought, and thank you for your time, for hearing me out. If you have any questions, comments, do write them in the chat. If you find the talk interesting, please cite us or tweet it to us.